Hi, Gen Bio. This is Dr. Fry. I am going to be walking you through the Enzyme Kinetics lab this week. So the first thing I want to draw your attention to is the equation for our enzymatic reaction that we are looking at in lab this week. So molecular oxygen plus catechol, these are our substrates or reactants that go into the reaction, will be converted to cis-muconic acid and water. Okay, these are our products. The enzyme that we're looking at using is polyphenol oxidase. This is extracted easily from potatoes. So one of the lab assistants for each lab chops up and grinds up potatoes and mixes it with a buffer to extract polyphenol oxidase, our enzyme. And catechol is provided for you in the lab. Of course, molecular oxygen is available readily all around us. And so as this reaction takes place, the conversion to the product, cis-muconic acid, can be easily observed because of one helpful feature. There's a color change from catechol to cis-muconic acid. Cis-muconic acid has a darker, much browner appearance to it than catechol does. So we can observe that happening with the naked eye, but more importantly, we can actually quantify it happening because we can use the spectrophotometer to monitor the amount of light that's absorbed at a particular wavelength, 430 nanometers. That is allowing us to observe the production of cis-muconic acid as this reaction takes place. So we can actually quantify the reaction happening in real time then by how much light is absorbed as the conversion takes place from catechol to our product. Okay? So that's the theory behind this week's lab. We are going to be putting the catechol and the polyphenol oxidase into cuvettes to mix those together. It's important to do that quickly, to mix it quickly so you don't miss the initial part of the reaction, because that is the point at which reaction rate is quickest, right? So when you put the cuvette into the spectrophotometer, what you're going to see is what we call a time course, okay? A time course is basically over time. So on our x-axis here, I've indicated time in seconds, how much absorption is taking place at each of those points in time, okay? So as you put the reaction in the spectrophotometer, you're going to get an absorbance reading every second, okay? And what you should see is then something that looks a lot like this, okay? Where at the beginning of the reaction, you first mix your ingredients and put it in the spectrophotometer, you're going to see that the rate of the reaction is quickest, okay? So you're going to see a pretty nice peak, hopefully. And then after time has passed, it starts to level off, okay? Reaction is still happening, but not as quick of a rate as it does in the beginning, okay? And so this point here at the beginning, we term the initial rate, okay? Makes sense. The initial rate, the rate at the start, okay? And so we can actually get a number to put to that, the slope of that line, by using a tangent button that's on the computer. And I'll show you this as we get to that portion of the lab. So we will take this slope and we will record that for different manipulations of this experiment. So basically what we're going to do is we're going to manipulate the amount of catechol that we put in. So we might change the concentration of the substrate at one point and keep one concentration of our enzyme. And then we might reverse that and have one concentration of the substrate and use different concentrations of our enzyme to see what the effect on the initial rate is, okay? So by the end of the lab, what you should get is two sets of data, okay, which you can graph in two different graphs, where you have, for the first one, varying concentrations of enzyme on your x-axis as you add more enzyme, you will progress further on the x-axis. And then you will plot that against the initial rate for each of those time courses that you recorded. Okay, so you will record the initial rate from each of the time courses, and you will plot those against the amount of enzyme that you used. And that would just be with a single substrate concentration. What you should hopefully see after acquiring and plotting that data is a line that is fairly straight and diagonal, increasing steadily as you increase the enzyme concentration. Okay? And this is because as you continue to add more enzyme, with enough substrate present, then you should continually see an increase in the rate at which the reaction happens, right? The second set of data is going to be looking at different substrate concentrations. So the substrate concentration, the millimolar concentration, is on our x-axis, and the initial rate is plotted on the y-axis. And we actually, what you hopefully will see is that the data takes on a slightly different appearance where you do see an increase in your initial rate with increasing substrate concentrations up to a point where you start to see that the rate of the reaction levels off, despite the fact that you might still be increasing your substrate concentration. Okay, and that point where it starts to level off, we call Vmax, or maximum velocity. And that's because that this occurs because despite the fact that you continue to add more of your substrate, there's a limited amount of enzyme that's present. Okay? So our enzyme concentration is the rate limiting factor here. Even if you add more substrate, all of the active sites on the enzymes are already occupied. They're already saturated with our substrate. So even if you keep dumping more substrate in, you cannot increase the rate of the reaction any further. Okay? So that's basically the theory behind this week's lab. One thing I want to stress is that for the students who are actively doing this in lab, you do have to be relatively quick when you mix the reaction and put it into the spectrophotometer so that you don't miss the initial rate. Okay? If you get it in too late, if you take too much time pipetting, you've already missed the peak rate of the reaction. So now I'm going to take you over to the spectrophotometer where we are going to watch this happen. So I've got my setup here, okay? I've logged in to Logger Pro and I have my spectrophotometer warmed up already. I have also, at this point, I've made up my catechol, okay? So the catechol, again, is the substrate. And that, when the students get it, it looks like this brownish, pebbly substance in the jar here, okay? And we mix that with 100 milliliters of phosphate buffer, which was also given to the students, okay? So that I've done, I've made that up. It's here in my jar. And I blanked and calibrated the spectrophotometer to that already, okay? So it has been blanked against this concentration, the full strength concentration of catechol, okay? So now what I'm going to do is I'm going to add my catechol to a cuvette, and we use 3 mils of catechol. So I'm going to just place that, hope you can see that here. I'm going to place that in my cuvette. Okay. And I'm going to use 50 microliters of my enzyme. Okay. If you remember, the enzyme was extracted from potatoes. And so I have that. I'm keeping it on ice here. It's in a little test tube. Keeping it on ice so that the enzyme doesn't denature. I'm going to take 50 microliters. You can see I've already set my pipette to 50 microliters of this enzyme. And at this point, this is what I was saying, we have to be relatively quick so that we don't miss the initial rate. So I'm going to get everything ready here. I have my parafilm ready. This is what I'm going to use to cover my cuvette once I mix the enzyme with the substrate so that I can quickly invert the cuvette, mix it up real quick, stick it right in the spectrophotometer, okay, as quickly as possible. So here we go. And stick it in and hit collect. Hopefully we'll see a nice peak here. So you can see as the reaction is happening, again, we've got time in seconds on our x-axis, and the absorbance, we're looking at a wavelength of 430 nanometers. I don't know if you can see that, but you can start to see the reaction happening. It's got an increase to it, and over time, that absorption value will, well, we expect that it will level off. Okay, so let's just give it a little bit of time here and see what happens. And in the meantime, I'll point out that I have this tangent button already clicked here. I can click it off, but this is the tangent button, which will allow me, when I click it, to get a number for the slope here. So if I bring my tangent line, I don't know if you can see it moving along the curve there. Bring it a little closer. You can see the red line is the absorption value as time progresses. And then the black line is my tangent button. So I'm gonna just hover over the leftmost part of the curve, the initial rate. Okay, so I'm going to take that number then. So that number, when I hover over the leftmost portion here, is given to me up here. The slope number is 0.00742, okay? So I'm going to enter that into my lab manual. And the place that I enter that into is on page, well, on mine it's 54. I hope it's the same on yours, but it's table 2, okay? And it's looking at the table, the first column, it's the 100 units per liter reaction rate 1 is where we're going to enter that number, okay? So again, it was 0.00742. So enter that right there. And then each of the columns next to that are where we will do this exact same process again, okay? So I will repeat it a second and a third time in order to get 3 different data points, which we can then average to get the average reaction rate at the 100 units per liter enzyme concentration, okay? So that let me just take a minute to explain to you. The 100 units per liter is kind of an arbitrary unit, a measurement of the enzyme concentration, because when we had the enzyme made up, we don't actually know the concentration. We know that it was extracted from potatoes, but we have no way of really, we have not analyzed what the actual concentration of the enzyme was. So we're calling it 100 units, arbitrary units per liter. And then when we progress and we dilute that, the dilution that you will do, I'll just show you here, on the previous page, the dilution that you will do is you take 1 milliliter of that full strength enzyme that was taken directly out of the potatoes, and you mix the 1 milliliter of that with 1 milliliter of phosphate buffer, okay? And so that's a 1-to-2 dilution, and then we call that one 50 units per liter. And then we basically just do a serial dilution of the enzymes, okay? So we do the exact same thing. We take 1 milliliter of the 50 units per liter and mix it with 1 milliliter of phosphate buffer in order to get the 25 unit per liter enzyme concentration, okay? And we do that one more time. Again, it's just serial dilution. We go into the 25 unit per liter, take 1 ml of that, and we mix it with 1 milliliter of phosphate buffer to get the 12.5 unit per liter concentration. Okay, so that's how we make our dilutions then. And then when we do that, we repeat this process, okay, that we just did. I'm gonna pause, I'm gonna stop collecting data now. Oh, looks like it stopped it for me because I let it go too long. But so you, at this point, you can see that the absorption value has in fact leveled off, like I suspected that it would, and I told you that's what we would expect to see. So you saw the increase in the reaction rate at the beginning, and that over time, that rate slows, okay? It levels off. Okay, so we can then just take this one out of the spectrophotometer. You can see it's a lot darker than it was at first, which makes sense. So here was our catechol, here's our cis-cis-muconic acids. You can see the reaction has in fact taken place. We're gonna set that right over there, okay? So basically, we're gonna repeat this process with a diluted enzyme concentration. Like I just showed you, we're gonna dilute the enzyme by half. And then we will reverse and use the full strength enzyme, which was given to us at the beginning, and dilute our substrate. So I will take this catechol and dilute it by half. And so that's what you do on the subsequent page at table 3. If you look at table 3, you can see that you started with 100 millimolar of our catechol, our substrate, okay? Now we do actually know the concentration of that because we had pre-measured out the catechol. I showed you the vial of it already. That was pre-measured, okay? So we knew how much was in there, and mixed it with 100 milliliters of our buffer, okay? So we know that that's a millimolar concentration. So we started with this, the substrate at 100 millimolar, and we do 1 to 2 dilution. We take 30 milliliters of that, our full strength catechol, and we mix it with 30 milliliters of the phosphate buffer, right? Same buffer we used before. And when we do that, it's a 1 to 2 dilution, right? And then we continue to make serial dilutions, taking it from 50 millimolar down to 25 millimolar by just diluting the 50 by half again, okay? And take that 25 then down to a 12.5 millimolar concentration by diluting it again by half, just a 1 to 2. And then repeat that and repeat it again until we get all of our different concentrations of substrate. Okay? And so when we have all these different concentrations of substrate, then we repeat this reaction with the full strength enzyme and then look at the initial rate for those as well, okay? So I'm gonna just repeat this process one more time for you to see. I'm going to take my, I'm gonna take my enzyme here. I'm just going to take 1 milliliter of that, okay? And I am going to mix it with 1 milliliter of phosphate buffer. I have to be careful to change tips here so I don't contaminate things. Don't want to ever use the same tip for the enzyme as you do for the catechol or the buffer. Okay, so now I have diluted my enzyme by half. Okay, so this is the 50 units per liter enzyme. You can see it looks a lot paler than the full strength. Okay, so I'm going to take my 1 ml of catechol. Looking for my proper pipette here. There it is. Technical difficulties. Hang on one second. Let me just get it into. All right, so to do the reaction again, I just diluted my enzyme. I'm going to take 3 mils of the catechol, take a fresh cuvette, okay? Put my 3 mils of catechol in there. And we are going to combine it again with 50 microliters of the now diluted enzyme, which is 50 units per liter enzyme, okay? I have that here. I should put it on ice. Okay, so same thing. I've got my parafilm ready before I mix everything together so that I catch the initial reaction, okay? So we are going to pipette this in, mix it up real quick, put it in the spectrophotometer and hit collect. Hopefully I was quick enough. I don't know, the line's not looking so good. I'm not sure I was all that quick because I was fumbling with the pipette a little bit. But you can see with a decreased enzyme concentration, the peak on this, the slope on this line has definitely decreased, which we would expect to happen. There's less enzyme available to use in that reaction. And so you would not expect the reaction to happen as readily. Now it is still increasing. So we're gonna give it a little bit more time. But again, if I use my tangent button and draw it over to the initial part of that graph, I can take the slope of that line and record that then in my lab manual on table 2, okay, at the 50 units per liter reaction 1. Okay, so the number I get for that at this point is 0.00247, okay? And again, I would repeat that a second and a third time. We like to do everything in triplicate as long as we have enough time so that we get a good representation of the data. And if I did fumble a little bit and go a little bit slowly on the one, hopefully the second and the third would give a more accurate representation of the experiment, okay? So I think that's about it for today. I am going to also compile the data that one of the groups of students has already acquired. And so we are going to forward that to you as well, so that then you can enter that data into your lab manuals and process it just as I described to begin with the 2 graphs that you're responsible for making. So I'll bring you back to the chalkboard here and just rehash those one more time. So the 2 graphs that you have to do will be with the increasing enzyme concentration on your x-axis. That's what I was just showing you, where I took the full strength enzyme, diluted it by half. So we started with 100 units per liter, okay? And I diluted it to a 50 unit per liter. And if we had kept going, we would have made 25 units per liter and 12.5 units per liter, okay? So those would have been the different concentrations that we placed in our spectrophotometer here and record the initial rate. So that's the one graph that you will make. And the second graph would be with diluted substrate concentration, so the catechol. Same process, we're using different dilutions of catechol and one single concentration of the enzyme, polyphenol oxidase. Okay, so I hope that all makes sense. If you have any questions, don't hesitate to email either myself at cfry@lvc.edu, or you can also email Jen Thornsberry. She's the lab coordinator and has been wonderful about sending out these online labs for you all so far. All right, that's it for me. I hope you have a great week. And again, email if you have any questions. Thanks a lot.